Thank you to the Climate Science organisers and everyone who showed up and paid money to see this. So hopefully it would be a waste of money. So next slide. So first thing, we're going to start with an intro to me. Born in Leeds. Sorry, any Blaze fans. I did my undergrad at York, and then I'm now doing a PhD here in Sheffield, so clearly I'm allergic to leaving Yorkshire. And then I did my master's dissertation on something called quantum energy inequalities, and I'm now working on quantum field theory for the first time, so I'm going to get it tattooed this one. I like to refer to myself as a mathematician despite doing physics all the time. And there's a picture of me here running because I used to run back in uni, and everyone kept asking me, what do you find harder, running a marathon or doing physics? So I ran a marathon to prove them wrong, and let's just put it this way, I signed up for a second one. So there. Next. Okay, so just a few preludes before we start. Basically how his talk's going to go. So I'm going to try and skip detail. I just want to give an overview of everything so that if you make up on something during the talk that you'll find interesting, you can go and Google it. It's just going to be a general overview. I'll do what we call general relativity first, then quantum gravity. Hopefully it'll be enjoyable. If not, apologies. And it seems I've got the vibe totally wrong. But in case anyone wants to do a drinking game, so it's pint of size, every time I mention the word quantum, take a drink. So hopefully everyone's going to be half full by the end. So, the big question. Next. So, we have two competing theories for two very different scales currently. So, we have something called Einstein's theory of general relativity, which basically models gravity, how planets interact, and how things on the sort of human scale. So it models that fine. Right. Quantum mechanics, I can't model galaxies and planets, can't model human behaviour, but it is good for particles. So you can see that there's a mismatch there. There's something wrong. So quantum gravity is basically our attempt at trying to find something that explains it for every situation. And now you might ask, well, we've got two different theories that work perfectly fine for two different things. Why not just leave it like that? I mean, I'd be out of the job. So in this climate, that's not great. But basically, there's a few situations that we have to pay attention to. So black holes. Within black holes, under the event horizon, we expect quantum behaviours to play a part in sort of gravity. That was very slow. So it's going to be and the Big Bang. So I'm not referring to the cheesy American TV show here, but the actual Big Bang. So we expect at the start of the Big Bang, however long ago it was, that some quantum fluctuations will have played a part in how the universe has expanded, essentially. And these quantum fluctuations, which we don't really understand at the minute, whatever they are, could go some way to explaining a few unresolved problems. So there's something called dark matter, dark energy, which is very popular science sort of things. I'm not a cosmologist, so I don't really know too much about that. But there's also something called the Hubble tension, which is essentially a discrepancy between the measured rate of the expansion of the universe. So we know that we live in a universe that expands. So we took something called the cosmic microwave background radiation, which is from the Hawking's big things, measured the rate of the universe using that, and then measured the rate of the universe based on what we see in our galaxy at the minute, and there's a massive discrepancy. So something's wrong, basically. So this is what we need to fix it, essentially. Next. But before that, I want to go into just have a brief interlude and tell you that the way that you think about gravity is all wrong. Which is always a good way to start a talk, telling the audience they're wrong. But essentially, so the way that we think about gravity at the minute is called Newtonian gravity. So it's the way that's taught in schools. You think of something like the Earth as a big, heavy object, and everything's pulled towards the Earth. And also time's absolute, so time just carries on forwards. It can't change, it can't slow down, speed up, it's linear. Whereas Einstein's theory, which is the one now accepted, gravity is not a force that pulls things. Instead, gravitational sources bend the space around them that essentially create wells that objects fall into. So think of it as almost like you have like a bed sheet, you put a heavy object on it, it's going to create a well. If you put any, say, marbles on there, the marble is going to fall towards this. So that's how gravity actually works. It's bending the space-time. So it's not a force. And also time is relative, which means you put speed it up and we can slow it down in certain situations, which sounds weird because it is. So there's this quote that everyone uses in our fields that by John Wheeler. He says, "Space-time tells matter how to move, and matter tells space-time how to curve." And that's basically the one we live off of. You know, if we ever go to a party, that's the one we're quoting. So, as you can see here, this is the Earth and the Moon orbiting the Earth, and you can see that it's bending the fabric of space-time. The heavier the objects, the more it's bending it. So this picture of me looking absolutely thrilled here is me stood in front of the space-time diagram of a black hole. So a black hole, as many people might be aware, is a region of space where gravity is so strong, light can't escape. Actually, what it is it's an object so dense that it bends the space-time so much that it creates a sort of an infinite well that nothing can escape from. I actually have a very quick demonstration. Now, I know many of you probably won't be able to see this. I'll just put this down. I'll have my two helpers. So if you want to see this demonstration at the end, I will show you because it is quite... then. So if you pull this pipe, you imagine this is space-time, okay? And I've got, say, a planet here. Pull that on space-time, and it bends... Oh, I've lost my marbles from the phone. There. So that bends space-time. And let's say these marbles are particles, and we put them on and shoot them round, and as you can't really see it, but essentially they've orbited round and fallen into this well. So if I do it again, boom, that's almost gone. It's not a perfect demonstration, but the faster they are, the more the orbit will drop in, basically. And if we take that out, you say that we have a particle and particle interaction, and thinking that round, it takes a lot longer because the well's not as big. And this is one of the big issues with quantum gravity, is that we don't know how particles actually bend the space-time. Thank you.
Thanks. So that's this down.
So yeah, I wanted to come back to this point about time being relative because it's a relatively strange thing, no pun intended. Basically, what that means is we can in essence time travel. So there's two ways of thinking about this. There's something called the special relativistic sort of way and the general relativistic. Special relativistic is the faster an object moves, the slower its clock runs, essentially. So this is all observation. So if we observed something going across the sky very fast, its clock, for us, looks like it's running slower. Whereas our clock is fine. Now, if you were on that, it's going to run the same. Our clocks don't change. Essentially, so next slide. So one way to think about this is this thought experiment with what's called a light clock. So we have two mirrors and we have a photon and we shoot the photon between them. So every time the photon hits the top, the clock ticks. Every time it hits the bottom, the clock tops. So it's stationary, it takes this constant rate, it's got the same speed. And now if we move the clock, you can see that the time between ticking and topping is going to get longer. So the faster this goes, the more it sort of slows this clock down. Essentially. It's a weird phenomenon, and you have to go at like superluminal speed, so you have to go absolutely rapid to get any sort of noticeable effect. So I can't just go run outside and go, oh, well, I've de-aged myself. It's not quite how it works. Next, please. Why do we care about this? Well, there's a couple of reasons. So, for example, on the ISS, their clocks run inherently slower, so we have to correct for that. But the most important thing is GPS. Everyone uses GPS in their daily lives. So that's it. So the way this works is we send a signal from our phone or device. It goes up, it hits a satellite, and it bounces back down. We know how long that's taken, right, because we know what speed we're sending this signal up at, because it's on the speed of light. We do this with, so what we know is that it's going to lie somewhere on a circle of a certain radius based on its speed. Do this with 3 satellites to sort of triangulate our position. We actually need a 4th satellite though, because the satellites are going much faster than us, so their clocks run slow. So if we took it for granted, GPS would be useless. After, I think the stat is after 4 minutes, our position will be off by 50 meters, and after a full day, it would be 10 kilometers off. So we could be in the ocean for all we know. So we have to account for this, and we have technology to do that because we know how much, we can calculate how much the clocks are going to slow down, and we can just adjust to that. So that's how GPS works. So without GR, no GPS. Yes, yeah. And there's actually a fantastic movie, Interstellar, with Matthew McConaughey, which explains this really well. So popular science isn't necessarily famed for having explanations that are perfect, but this movie is probably the closest you're going to get to these effects. So, for those not familiar with the seller, in one part of the movie, they send their ship near a black hole, and they land on a planet there. Now, a black hole obviously is this incredibly heavy object, incredibly dense. It has a heavy gravitational force. So near there, their time's going to run slower. So in the movie, I can't remember the exact stats, but I think they're on there for about an hour, and 7 years have passed back on Earth. And this is where the observational thing comes into play. They don't age 7 years because for them, time's only gone 1 hour, but for everyone else, it's on 7 years. So that's why when he goes back, everyone else's age, and his daughter's now older than him. So it actually does. So this movie does actually explain it very well. And that gargantua, the black hole there, was actually modelled by one of the people that basically wrote the book on GR. So he was the science advisor, which is pretty cool. And yeah, since the 11 years since we've released, it's only been about 95 minutes on that planet, essentially. So it's quite an effect. So now we've talked about why GR is important and whatnot, but how did we validate this? How did we know it was true? So back in 1919, back then, if anyone remembers, it was the first experimental validation of GR. So we thought, based on Newtonian physics, that Mercury orbits the sun in this elliptical shape and it shouldn't move. And yet when a chap called Eddington basically looked at a solar eclipse back in 1998, he saw that light was bending and essentially found out that Mercury precesses, easy for me to say, which means that this orbit bends as well. So it's not on this fixed orbit. And this was basically validation that GL works. More recently, we have something called gravitational waves. So these were theorized by Einstein back in the 20s. And we, I think in about 2014, actually finally observed one. So gravitational wave, what is it? Well, because we know that space-time is this like material, think of a boat going through water. When a boat goes through water, it creates ripples that go outwards. That's what a gravitational wave is. So when objects move through space-time, it creates ripples in the space-time, and those are gravitational waves. And back in 2014, we actually observed one. There we go. Let's look back again. But basically, they changed. So that's not what it sounds like, but they changed it in because we can't hear it because of wavelength. But they've changed it into a form where we can hear it. So that was back in 2014, and this is LIDAR, the station that detects it. And you can see the sort of scales, like the arms to detect it are about 2.5 miles long. And it took so much to do it, and we've not observed very many at this point. And then that diagram up there is just sort of showing the rippling effect. So, on the mechanics. Now, obviously, we've just had a very good talk, which has explained some of this, so I can sort of skip over some of it. But essentially, there's 5 main points that I wanted to sort of bring to your attention. So there's something called Young's double slit, which was somewhat the first experimental validation of quantum mechanics. We have the uncertainty principle, and has anyone heard of Schrodinger's cat? I'm guessing some people have. It's a very famous thought experiment. And then everything's probabilistic, which I'll tell you. And one of my favourite quotes of all time is from the quantum physicist Richard Feynman back in the 60s. He basically said that nobody understands quantum mechanics, and if someone tells you they understand quantum mechanics, they're either lying or crazy. And I still believe this there. And then I'm going to touch on something called quantum field theory, which is more where my work lies, but I'll explain what that is in due time. So the double slit. In case anyone isn't aware of this, so this was back in, I think, about 1820. Thomas Young, I think his name was, he shot an electron beam gun, this double slit, and what he observed was this sort of wave pattern on the board behind it, which this essentially, and the previous talk already touched on this, showed that particles behave like waves. So this whole thing of it can go through both at once until you observe it, and then it's one. So so this was actually sort of before quantum mechanics was really a thing, by about 100 years. If you put a detector on one of those slits, all you would see is a single particle being shot through one. You wouldn't see that pattern. So until it's observed, it can be anywhere on there. Once you observe it, it is stuck there. Which brings us nicely to Schrodinger's cat, actually. So there's a bit of a misconception with this paradox. So the thing that everyone always likes to quote and roll out is, oh, Schrodinger's cat, the cat's both alive and dead. It's not. So the way it goes, the actual paradox, and this was something that Schrodinger sent to Einstein in relation to that 1935 paper where he basically said this is rubbish, and this was Schrodinger's answer to it. So he puts a cat in a box, and I don't think he actually did this, frankly, and puts a radiation source in there, and a Geiger counter, so that's our detector, and a hammer connected to the radiation source, which will smash a flask of poison, killing the cat. So the idea is, if the detector detects any radiation, so there's just one particle decay, smashes the glass, kills the cat. But if it doesn't detect the radiation, then theoretically the cat should be alive. Now the point is that the cat is not both alive and dead, it's that until we observe that event, the cat can be either, but once observed, we'll know that the cat is either alive or dead, essentially. So what he said about that was that an indeterminacy originally restricted to the atomic domain turns into essentially observable macroscopic indeterminacy, which can then be resolved by direct observation, which basically means indeterminacy on the quantum level can sort of go on to the sort of, when he said macroscopic, it means sort of hour scale until observed. So it can be either level until observed, eventually. So that's what Schrodinger's cat experiment actually says. So, quantum field theory. Is he just doing quantum mechanics in a field? Not quite. So, there's a bit more nuance to it. And which is good, because otherwise I wouldn't be here. But actually, it's this mathematical foundation that we've built up, where it takes quantum mechanics, which deals with individual particles, and transfers it to these things called fields. Now, think of fields as these things that affect every particle across all of space-time. So, a field, for example, might be the electromagnetic force. So a magnet is a field itself because it's creating a force that's pulling things towards it. And then we basically describe particles, such as electrons, photons, whatnot, as excitations, whatever that means, of these fields. So it's basically high energy levels. In A-level physics, and like taught with an atom, you have these concentric rings, and if you energize it, the electrons, subatomic particles, join up said rings. That's essentially excitation. And that's kind of what quantum field theory is. Now, there are issues with it. So, for now, we have only developed quantum field theory in flat spacetimes. So it only works in flat spacetimes. So if a flat earther ever tells you the Earth is flat, you could say, yes, you must be a boson. And that's not a euphemism. Because, as it sounds, it only works in flat spacetime, but we are working to sort of get into a general post spacetime. So, just to labour the point a bit more, in case you've not already got sick of hearing it, why can't we just add the theories together and call it a day? Well, there's certain things that happen. So there's something called the black hole information loss paradox. So this is where quantum gravity really comes into this. So, general relativity, or gravity, is deterministic. If we take an initial state, it always evolves to a final state. We can always work out what that initial state was from the final state. If we take a black hole, its information here is its energy, momentum, and mass and angular momentum. It's not more. We take two black holes with different values of those. Now, there's a process called Hawking radiation, which is a semi-classical thing. Don't need to worry about it, where any black hole can basically evaporate. Now, if they both evaporate, they evaporate to nothing, everything's disappeared. How do we know which black hole we started with? And does that not break the determinism of GR, where for every final state we can tell what initial state was? So information is being lost, and it shouldn't be. So that's one of the issues that quantum gravity seeks to resolve. There's another way of thinking about it. So if I throw myself into a black hole, which I haven't done, I have information about me. Black hole evaporates. Where have I done? Essentially. Who knows? I don't want to try it. So this sort of leads us quite nicely into quantum gravity. So the bad news is we're not anywhere near any theory of quantum gravity. Even worse news is we don't know which way to go. So there's tons of different theories. I think Wikipedia notes it down as there's about 100 different ways that people are attempting to unify the two. I think the big ones to pick up on, so I think a lot of people might have heard of string theory. It's the one that everyone's talked about. So this class called the theory. It's sort of a theory of everything. It seeks to unify all the fundamental forces into one big theory. I don't know, one big equation or something. But there are other things. So string theory works by essentially, instead of particles being particles are strings, these one-dimensional strings, and we technically live in 11 dimensions or something like that. And these strings vibrate through these 11 dimensions. It's all very complicated. Mathematically it works. Physically I think it's a lot of hogwash. Anyhow, and that's kind of it. And this predates, so string theory actually supports something called a graviton, which is thought to be the fundamental particle for gravity. So how with electromagnetism, the photon, the light particle, is the particle that basically mediates any force. So it's think of it as a connector. And we have gluons for the weak interaction and bosons/fermions for the strong. So we have these. We think there should be one for gravity because it's this action at a distance principle. One thing happening can't simultaneously, we think, affect something else. There has to be something that connects them. This is what we think the graviton is now. The graviton is massless, so it goes in the speed of light, so it happens pretty much instantaneously. But there are other approaches that are less ambitious. So something called loop quantum cosmology and loop quantum gravity. Basically what that does is it breaks down the space-time and says each individual space-time is made up of a loop that we weave together into some fine fabric, and you can look at it in sort of chunks. I don't really know too much about that. It's all a bit too complicated for me. And then that seeks, so that is a famous offshoot, which is with quantum cosmology, which is sort of working with the cosmic micro background radiation. But then the reason I'm here is I do something called quantum field theory curved space-time. So that's where we take the quantum field theory in flat space-time and just basically try and curve the space-time. It's not as easy as it sounds. And there was a lot of issues with a lot of these different ones. So QSCCS, as I'll call it from now, doesn't predict for graviton. It's very much semi-classical. So basically it works by saying, okay, we'll treat gravity as classical and particles as quantum and see how they interact. It has its issues. So it's represented by basically you have curvature of space-time on one side of the equation, quantum matter on the other. Now quantum matter is represented by what's called an expectation value, which is essentially the average chance that a particle is going to be in any given position. Now we find in these theories that we get an answer to that of infinity. So what's it mean that a particle is going to be at infinity? The probability of that particle being there is infinity. Doesn't make sense. So this is one of the things I work to try and fix. It's called problem free normalization. And then just wanted to briefly touch on the graviton. So again, as I said, it's that sort of fundamental particle that mediates the interaction, we think. The bad news is, it is very unlikely that we'll ever detect it. So there was a thought experiment that went about a few years ago. Basically said we'd need a detector about the mass of Jupiter orbiting a neutron star at 100% efficiency in ideal conditions, and even then we'd only observe a graviton once every 10 years. That's with the caveat then as well that we could build a neutrino shield around this detector that protects it from neutrinos, but the size of the shield we'd need would be so big it collapses into a black hole. So it's just not that. So basically, we're never going to observe this. But theoretically, we think it should exist. You actually have developed bands, so we now believe that it's massive, it has mass, and not massless, so work instantaneous, which has been done with a few servers. The messenger probe that we sent out into the galaxy somewhere, basically taking some observations for that. And then another track that people try to take, so there's this lab in Nottingham, actually, that do something called analog gravity, which I think is pretty cool. So essentially what they do is they use situations we can develop on Earth to try and mimic the conditions in the universe. So this is what they call the big bathtub. So here, what we see on the top left is they've created a vortex of water in this bathtub and they've shone light across it. And this actually mimics very well how a black hole behaves in space-time. So they've been able to find out information about how stuff behaves around the horizon, at what point it's going to drop in, at what point it will stay out, just using water. which I think is pretty cool. And I think you can go visit it and see it. And actually, a bit of a somewhat shameless plug for the Pint of Science. There's a very good video on the Pint of Science YouTube video where they interviewed Silke Weinferner, who has personally put this together, shows how it works and everything. So I'd recommend you go watch that because I think it's pretty cool that these quantum effects that otherwise we won't be able to see, we can model in basically what's a big bang, essentially. So just one last thing, or basically what I do. So if you remember the quote, space-time tells matter how to move, matter tells space-time how to curve. So I'm the latter. I work on basically, if you take a matter model, what's it going to do to the space-time? This is something called back reactions. Highly non-trivial and leads to equations that look something like that. They're absolutely horrible, and I have to stare at them daily. So please, someone spare a thought. It's just these huge things on my computer that I have to sit through and try and solve these like 16 coupled differential equations that will take about, and I think it was something like 96 hours to run. Yeah, it's a lot of fun. But this is basically, these are modelling quantum matters for classical. I feed it in, I try and sort of work out how it tells space-time to move. The idea is that you're meant to be able to do this over and over until it sort of tends to a set limit. But this has taken 2 years to do once. So I don't think it's going to happen somehow. Unless I can extend my age infinitely. And the last thing that I just wanted to end on is apparently it goes down quite well when you show people where you get to work during this. So here's me in space, and I can switch a black hole. Here's me in CERN's particle accelerator. I've cloned myself, fired the cells against each other. So when they did this with electrons, they got the Higgs boson. Now let's say that got the Higgs boson. Last of all, here's me throwing myself into a black hole to see what happened. It wasn't pretty, I'll tell you that. I was sore in the morning. But in reality, this is what I actually do. I sit at the computer, looking depressed, for hours on end, pretending to do work. And that's everything. Thank you.